There are two types of chi-squared tests. There's the goodness of fit test, and then the test for independence. Today we're going to talk first about the goodness of fit test, and then the test for independence. So similar to the t-test, where you have a one-sample t-test and a two-sample t-test, the chi-squared goodness of fit test is a one-sample test, and the chi-squared test for independence is a two-sample test. Now it's testing for a different thing than we are in a t-test. So in the chi-squared goodness of fit test, what you're doing is checking to see if your sample matches known information about that population. For example, if we look up worldwide statistics on eye color, you might see that like 20% of people are blue-eyed and 7% people are green-eyed and 68% of people are brown-eyed or whatever, right? You have some known statistic about how the ratio of eye colors in the world. Everybody feel okay with that being a thing that you could look up? If I then sampled this classroom and recorded down eye color, I could test to see if my sample matches the known distribution, right, of eye colors. That's the goodness of fit test. Is everybody okay there? If you're checking to see if a sample matches a known distribution, that's what you're checking. That's a goodness of fit. If you're looking at testing whether two separate variables are related to each other, if there's an association, like a cause and effect relationship, like you're looking to do in your IA, you would use a chi-squared test for independence. Okay, so that's you're sampling two different variables and trying to test if there's a relationship between the two variables, i.e., if one depends on the other. Everybody feel okay with the difference between the two types of tests? Just in theory, right this moment. Everybody okay? All right. So let's walk through how to do this goodness of fit test with an example. So let's say that we take M&Ms. The company that makes the M&Ms has a known distribution of color for their M&Ms. When they make their M&Ms, 13% are brown and red, 14 are yellow, 16 are green, and 20% are orange, and 24% are blue. So when they make their big batches of M&Ms, that's the percentage of M&Ms that they get. They mix them all together, and then they, squirt them into bags, right? Let's say we want to test to see if, M&M's published distribution of colors actually matches what you find in practice. Okay? So let's say we bought a bag of M&Ms and we counted up how many we had of each color. So we had 9 blues, 8 oranges, 12 greens, 15 yellows, 10 red, 6 brown, for a total of 60 total M&Ms we counted up in our bag. Everybody so far so good? What we want to test is, does this distribution of observed colors match the known distribution of colors? Okay, that's what we're going to be trying to do. So everybody feel okay with the goal and what we're trying to do here? I'm going to try to be a little bit more big picture before we get granular. Is that okay? Yeah. So the goal is, I want to check to see if this observed distribution of colors matches the known distribution of colors. That's what we're testing for. So far, so good? Okay. So, for example, if I look at my sample that I took, I found that 15% of my sample are blues. Everybody's okay with that? Because I just took 9 and divided by 60. I could do the same thing for orange, green, yellow, red, and brown. Everybody's okay with that? Now, one thing I could do is I could now just do a t-test and check with, is the null hypothesis being the probability that the blues are 24%, and that the alternative is that it's not 24%. It could be bigger, it could be smaller, but it's not 24. And then I could do that for each color. It's a lot of t-tests though, right? You guys see what I'm saying? Because we potentially have to check this for each color. Not a lot of fun. Instead, what we can do is we can do it all in one shot with this chi-squared goodness of fit test, which is what we'd rather do. Is everybody so far so good? Okay. All right. So this new goodness of fit test, let's talk about what we're going to be doing. We want to first start by writing our null and alternative hypothesis. For a goodness of fit test, the null hypothesis is always in the form of the observed distribution matches the known distribution. Now, in practice, you say what the distributions are, right? Like the observed distribution of M&M colors matches the known distribution of M&M colors. But you'd say something like that. The alternative is that it does not match, that the observed distribution of M&M colors does not match the known distribution of M&M colors. Or the way I stated here equivalently would be the known distribution of M&M colors is correct, right? Meaning that what we got in our bag matches the claim the company makes. So everybody's okay with the null? Always the same. It's a no-brainer, right? The observed observation matches the known observation, or the observed distribution matches the known distribution. Always in that format. Just say what the distribution is, but fine. And then the alternative is always, it doesn't match, or the known distribution is not correct. All we're doing is adding the word not into the alternative. They're the easiest two hypotheses to write because you don't have to think about it. As long as you recognize the question is like a chi-squared test, the hypotheses should be really easy to write, as opposed to the t-test where you really got to kind of read it to get the null and alternative hypotheses correct. You know what I mean? Especially the alternative. Everybody so far so good? Okay. So the other way you could do it is you could do it numerically, right? I would not choose to write it this way because it's kind of yucky, but it's just saying the null would be the probability for blue is 24, probability orange is 20, probability green is 16, et cetera, et cetera, et cetera. And the alternative is at least one of those probabilities is incorrect. Where did these numbers come from? They were given to us in the original problem. This was the stated distribution of M&M colors by the company. Does everybody feel okay? We're going to actually do this in live and in practice for our activity on Friday. While I'm on the subject of this, peoples with peanut allergies, are there any peanut allergies in the room? How bad is your peanut allergy?
It's not. I'm not
Can you be in the same room as peanut M&Ms? Okay. Just don't eat them. Okay. Anyone else that I have to be concerned about? Okay. Very good. That's easy enough then. Okay. Everybody's okay with the other way you could write it symbolically? You do not need to do it that way. I'm just stating that we could. I would write it in words because it's like a no-brainer. It's like a Mad Lib. You just fill in the blank and move on. Let's see. Okay. So the next thing we need to do is we need to calculate, okay, if that null hypothesis is true, what should have been our observed number of each color, right? Assuming that the null hypothesis is right and that the bag contained 24% blue and 20% orange and 16% green and so on and so forth, how many of that 60 should have been blue? How many should have been green, etc.? Everybody okay with that idea? What that's called is the expected count. So the expected count is what we should have gotten if the null hypothesis was true. That's going to look like that. So all we're doing is taking the known distribution or the known percentage and multiplying it by our sample. Everybody's okay with that? Expected counts can be decimal. No problem there. Even if we're talking about the number of M&Ms in a bag, it's okay. It can be decimals. Everybody's good? So we just took the total of our sample times the probability of getting each of the categories. Everybody feel good? So if we look at this, we have our observed versus our expected. Everybody's okay? That's just me collecting the data and putting it back together again. Looks good? Now, if I wanted to compare this, maybe I make like a bar graph where the blue bars are the observed and the red is the expected. Or maybe that's orange. What color do you think that is? Orange? We'll call it orange. Yeah, I think that's the color. So if I look at that, it seems kind of different, right? I don't know. Is that different enough to say that the known distribution is wrong? Probably, I don't know. It's something, but I don't know that that's evidence to say one way or the other if the known distribution is not correct. You guys agree? Okay. So instead, what we'll do is we're going to calculate what's called a chi-squared statistic. And basically what that's going to be is it's going to be a numerical measure or numerical representation for how far away are the expected counts or our observed counts from our expected. Everybody's okay with that idea? That's basically what we're doing, is calculating how far away the observed are from the expected. So the bigger that number, the less likely that the known distribution is correct. The smaller that number, the more likely it would be. Does that make sense? The distance is big. That means the two things are far away, means that probably the known distribution is wrong, or you got a weird sample, right? All right, continuing on. So the way that we calculate this chi-squared statistic, the way we calculate those distances, is we do observed minus expected, and then we square it to get rid of the negatives, and divide by expected. We do that for each category, so we do that for blues and reds and greens all the way through, and we add up all those, and that'll give us this chi-squared statistic, or we call that chi-squared calculated. So looking at what we have here, we would do observed minus expected divided by expected for each category. Is everybody okay with that? And then we add them all up. And that 10.180 would be called our chi-squared calculated number. So that's the number we calculate. That's our chi-squared statistic. We're going to then use that number to determine whether we found evidence in support of our null hypothesis that the known distribution is correct, or evidence in support of the alternative that the known distribution is wrong. Everybody's good so far? Okay. So let's talk about how we're going to use this number. So I said earlier that this number kind of represents a distance in how far away the observed are from the expected, right? And the bigger that number is, the further away it is, that's more evidence for the alternative. The smaller that number is, the closer they are together, the more evidence for the null. Yeah? The question should become, well, how big is big and how small is small, right? I look at that 10.18. I don't know, is that a big number or is it a small number? What are we saying here? We had the same issue with the t-test, right? Is that p a big P or a small p? I don't know. Guess what we did? What did we do with the t-test? We compared it to the level of the significance, the alpha. That's correct. We'll do the same idea here. Okay? We'll do the same idea here. So I got to build up to that, but that's where we're going now. Okay? It's talking about how do we know if this 10.18 is that big or is that small? What kind of evidence is this really providing for me? All right. So it turns out that for the t distribution, it always looks that same kind of bell-shaped curve. The chi-squared distribution that we're doing here its shape depends on the degrees of freedom. So if I think about the degrees of freedom, that's basically just the choice. So if I look at my variables that we had before, we have 1, 2, 3, 4, 5, 6 variables, right? If I was to pick the first variable, how many choices do I have? I'd have 6 choices if I was just going to pick one of them, right? For the second spot, how many choices would I then have? 5, because one of them's gone. And the third choice I'd have, and the fourth choice, the fifth choice, and the last choice. But is there really a choice for the last one if there's only one choice? No, right? So that the first 5 spots I have a choice, but the last one is decided for me because it's just whatever's left. Did you guys see that? So what that says is that there's 5 degrees of freedom because I have a choice up until the last one. So the degree of freedom is always going to be the number of categories minus 1 for a goodness of fit test. It changes for independence because we have 2 variables. We have like a two-way table thing going on. Does that make sense as to what the degree of freedom is really saying? And now, depending on the number for the degrees of freedom, the shape of our chi-squared distribution changes. Okay? This is not something you'll have to calculate. It's not something you'll ever have to draw. The calculator will draw it for you. Okay? But what this matters is that if I'm looking at a 4 degree of freedom and my chi-squared critical value is 4, the percent of the curve that's bigger than 4 is different for the orange graph than it would be for the blue graph, right? If I look at the probability, the area under the curve is going to be different for each of these chi-squared curves for different x's, right? That's the point that we're trying to make here. So the shape of the graph really matters to us. That's why we need to have that degrees of freedom. If you enter the wrong degrees of freedom into your calculator, it's going to get you the wrong number. Okay? So that's going to be one of the inputs into our calculator. Now, just because I can compute a chi-squared value doesn't mean that it's going to be a valid test. So there are two criteria that we must check for before we make our final analysis to make sure that the chi-squared test we're about to do is valid. So those two criteria is our random sample making sure it's not too big, and that our expected counts are big enough. Okay? So the thing we need to check, the first thing is that our random sample is not more than 10% of the total population. So for M&Ms, in our M&M example, we had 60 M&Ms in our sample, right? 60 M&Ms is 10% of 600. Are there more than 600 M&Ms in the world? Yup. We've made that condition. We've shown that 60 M&Ms is not 10% or more of the total population. Everybody feel good? The second thing we need to check is that the expected counts are all greater than 5. So if I go back and look at my expected counts, the smallest expected count was 7.8. That's bigger than 5. So this passes both of the criteria necessary for a valid chi-squared test. So now that we've done that, we can go ahead and use this number to say something about our hypotheses. Everybody's okay? We have to make sure we check that, though, before we make any conclusions, because if you don't meet those criteria, you can't draw any conclusions. You just have an invalid test. Everybody's okay? Okay. So we've been talking about how do I know if that 10.18, that chi-squared number, is that a big number or a small number? So again, we're going to do this using a level of significance, just like we did for the t-test. So we're going to use that same alpha to represent the level of significance. We're going to state in the problem what the level of significance needs to be, whether it's 5% or 10% or 15% or something else. Everybody's okay? So the two ways that we can then analyze that chi-squared number is, one, we can use that chi-squared number to calculate a probability, like what is the area under that chi-squared distribution that is greater than, in our case, 10.18, and compare it to our alpha. Or we can figure out, okay, if I draw in the area under the curve that's like, say, 5%, what x value is that starting at? And then compare that x value, we call that chi-squared critical, to the chi-squared calculated value we had earlier. We'll draw some pictures in a moment to kind of illustrate the two different ways of doing this. In general, just like the t-test, where you could compare the t value with the t critical, or you could compare the p with the alpha, and you have a choice, you could do either one. We have a choice here. We'll almost always do the compare p to alpha for the chi-squared also. Because if you gave me a chi-squared critical, you'd also have to give me the level of significance with it. So I can just compare p and alpha. All right, let's continue on. All right. So to get that chi-squared critical value, or that, like chi-squared 5%, that'd be often the way you'd write it, saying that the level of significance is 5%. So that would be something the chi-squared critical value would be something given to you in the problem. You would not ever be responsible for calculating that yourself. It'd just be in the problem instead of the level of significance. But the way they almost assuredly write it is chi-squared 5% or something. So the level of significance is kind of baked into it. Do you know what I'm saying? Okay. So if I'm comparing chi-squared and chi-squared critical, if our chi-squared calculated, that's the number, that's the 10.18 that we got, is bigger than the critical value, that is evidence in support of the alternative. So if we think about, we'll do it in a second. There's a picture coming, I think. If it's the reverse, if the chi-squared calculated is less than or equal to the chi-squared critical, that is evidence in support of the null. Again, that's something you just have to have memorized, right? This criteria. So, for example, this is our distribution for 5 degrees of freedom. Here's our chi-squared calculated value, that 10.18. This area under the curve in blue, that represents our p-value. If I look at the chi-squared values for different levels of, or for different probabilities, so if that probability is 0.15 at 5 degrees of freedom, that would be like here at 8.12. So you'd be looking at that area there. If the degrees of, or if 5 degrees of freedom, if the alpha is 10%, if the level of significance is 10%, I'd be looking at a chi-squared critical value here. So this area afterwards is like 10%. And at 5%, the chi-squared critical value would be here at 11. And the area under the curve after 11 is 5%. Okay? So let's say that we did, if we're doing 5%, our chi-squared critical value is 1107, which is greater than our chi-squared calculated, that 10.18, which is in support of our null hypothesis, saying that, hey, even though this sample that we took, the colors didn't seem like they matched the distribution, they're close enough. Is that okay? We still haven't talked about how to do this on our calculator yet. I'll show you that in a minute. The other way you can do this is with a p-value. So if their p-value is less than alpha, then that is support for the alternative. If the p-value is greater than or equal to alpha, that is support for our null. Notice that these inequalities are opposite for chi-squared calculated versus chi-squared critical. The inequalities are going the opposite direction, which is often a thing that confuses students. You just got to like memorize it. But if you think about it, it should make sense. If chi-squared critical is before chi-squared calculated, the area under the curve for chi-squared critical, the alpha, will be bigger than the area under the curve for chi-squared calculated, the p, right? Even though the critical is less than the calculated. Does that make sense? I have a picture coming up that helps. So far, so good? You're like, well, we'll see when we actually do this in practice. All right. Here is the two conditions for validity. So the randomness condition is that you did a well-designed random sample or a random experiment. And you have your sample is not more than 10% of the population. And then large counts is that all the expected counts are bigger than 5. And we kind of confirmed that with our M&M thing a minute ago, right? Two little tips, common mistakes I'll see students make, is the expected counts need to be actual counts. They can't be probabilities. So in our M&M example here, we go way back to the beginning here. What you don't want to do is say, okay, 9 over 60 is like, 0.15%, and then compare 0.15 to 0.24. You can't do a chi-squared test with probabilities. It has to be with counts. You guys see what I'm saying there? So that's a common mistake to make. Get through back to here. Oops. Now, you stupid machine. Make sure I'm not going too far. Okay, there we go. And the second is, when you're doing the large counts check, that you have to make sure you're looking at the expected counts, not the observed. Very common for students to just look at the wrong set of data. All right, so our summary is we check our two conditions, and then we write down our null and alternative hypothesis. We find our expected counts. Calculate the chi-squared statistic. Compare that then to the chi-squared critical, or using our degrees of freedom, find the p-value and compare that to alpha. Everybody's okay? So that's like our summary slide of what to do. Let's look at our in-class example. For this, I invite you to take out your calculator to follow along at the same time. So it says you open an economy bag of Skittles that has 500 candies in it. You take the candies from the bag and note their colors. You wish to compare your sample count to the percentages given by Skittles in the table below. So we are given a known distribution, and then what we found in our experiment or our sample. We'll start by stating the null and alternative hypotheses. Can somebody tell me what the null hypothesis would be for this? The known distribution of Skittle colors is correct. Or you could say matches the observed distribution of Skittle colors. Either is fine. What would the alternative be? Good. Both of you guys said different things. They're both correct. Good enough. Thank you. So far, so good? Okay. It says then, enter the expected counts. And it says to just show your work for the green Skittle calculation. Let's just do this on our calculator here. So the way I would do this is I would use my table here to do this. So I'm going to enter my observed counts into L1. And then into L3, I'm going to enter the known distribution as a decimal. Everybody so far so good? Now to create my observed count or my expected counts, I'm going to move my cursor so that it's on the title L2. I'm going to press enter, and I'm going to just take my probability from L3 and multiply it by the total in my sample. So I'm going to do 500 times L3. And then just press enter. And whoop! There's all my expected counts in one shot. Joey, you're welcome to sit in a different seat while we're doing these calculator things at the board.
I can see that.
Or bring your glasses. I just did 500 times L3 because 500 is the sample size. And then, isn't that nice?
Yeah.
Because 500 is the sample size. There are 500 total Skittles. So if I expected 19.7% of that 500 to be green, I'd expect 0.197 times 500 to be that. Because you don't have your cursor on the L2 title, you have it in the first cell. I'm guessing anyways, Grace. Everybody's okay? Grace, did it work now?
Yeah.
Great. All right, state and verify both conditions. So the randomness condition, I need to show that 500 is less than 10% of the total population of Skittles. 500 is 10% of what? 500 is 10% of what number? 5,000? Just 5,000? You multiply by 10? Right? Are there more or less Skittles than 5,000 in the world? Way more, right? We've satisfied the randomness condition. The second is the large counts condition. Here we need to check that our expected counts are all greater than 5. What is our smallest expected count? 97.5, right? Is that bigger than 5? Then we're good. So to do the large counts, you just check the smallest expected and show that that's bigger than 5. You say the smallest expected count is blank, which is greater than 5, so we're good. Same way for the randomness. You say that, this sample is 10% of this number, which is way less than the total in the world for this. Everybody's good? Okay. Using your calculator, find the chi-squared statistic, degrees of freedom, and p-value. So let's do this once with kind of by hand with our calculator, and then we'll do it with the built-in feature afterwards. Sound good? In case you have to do something where you have to show some intermediate work, like on a quiz or a test, hint, hint. So to do that intermediate work for my chi-squared statistic, I'm going to do this in the table. So I'm going to go to L4. I'm going to press enter. And if you remember, the formula for chi-squared was observed minus expected squared divided by expected, and we have to add those up for every category, right? So in L4, I'm going to do parentheses. L1 was my observed, minus L2, that was my expected. Close my parenthesis and square it, divided by expected. I just said observed and expected because I don't know what list you guys put your stuff in, right? And if I press enter, whammo! There they all go. So those are all the intermediate values. Everybody's okay? No? One moment. That's fine.
We should have. He's here on top of this stuff.
Okay. What's the best way to add up these numbers then? I do the one variable statistics on it, right? So I'll do the one variable statistic on L4. So stat, calc, one variable stat on L4. And this 5.60, or I should say 5.61, is my chi-squared value then. Okay. Alternatively, did you do it on L4?
Yeah.
No, that's what I did. Alternatively, the calculator can do it can answer all these things in one shot. Oh, did you have a line for the total?
Yeah.
Oh, you goobers, there's no total. That's not a category. The colors are the categories. That would do it. Ay, ay, ay. All right. Let's watch this. If I press stat and I go to tests and I scroll down, way down deep, I see option D is chi-squared GOF. That stands for goodness of fit test. Press enter. I'm sorry, what? I don't know. I just scrolled. Just use up. Just go up and it'll cycle back to the bottom. I don't know how to get to D. Just use the arrows.
No, like DF on the
Oh, yeah. What is the degree of freedom? 1, 2, 3, 4, 5 categories. 5 minus 1 is 4. And I put my observed in L1, my expected in L2. So I hit calculate and whammo, there's that same chi-squared number we just saw. There's my P. Everybody's okay there? All right. So given the chi-squared critical value is 13.277 at a 1% level of significance, what can we conclude? We can either compare 5.6 to 13.27 or 0.23 to 0.01. It doesn't matter which one comparison you make. Typically, I just use P's and alphas.
P is greater than A.
P is greater than alpha.
So we fail to reject the null.
Let's go back and find, there we go. P greater than alpha. We accept the null. That's evidence in support of the null. Fail to reject is the same thing, yeah. Yeah, I like writing evidence in support of, but what do you guys think? Yeah?
Easier than the other ones.
Yeah. So here's another one. It's the same idea. I'm not going to do it right now. Is that okay? All right. What I want to do next. Yes, sir. It's the number of categories minus 1. So there are 5 different colors. So 5 minus 1. All right. Next, let's talk about chi-squared for independence. Test for independence. So there's a second version of the chi-squared test. So this time it's going to tell us if there's an association between the two variables. Okay? It's no harder to do than the previous one. Basically what we're going to do is check to see if these two variables are independent of one another, i.e. is there like a function relationship, right, where you have an independent and dependent variable where one depends on the other. So our null hypothesis, the way we write this, is always the same. Variable x and variable y are independent of one another. You must have the word independent in your null hypothesis or it is wrong. If you substitute any word for independent, I will mark it wrong. Everybody's okay? Now, you recognize that when I say variable x and variable y, you have to like substitute in the variables in the problem, right? You just can't say x and y. It's like a Mad Lib. You're just filling in the blank there. Everybody's okay? So if it's shoe size and height, you'd say shoe size and height are independent of one another. Everybody's okay? The alternative is just that they are dependent. So you say again, shoe size and height are dependent of one another. Easiest hypotheses ever to write because they're always like the same format every single time. You don't have to read the question quite as closely as for the t-test. Feel okay? Okay. The chi-squared test is still basically doing the same thing, looking at the distance from our expected to our observed. We'll then use that to calculate a chi-squared and compare that to some level of significance or chi-squared critical to test if our null hypothesis is correct. So first thing we do is we're going to have to organize our data into some kind of two-way table. So let's say we did a random survey looking at the average number or average hours of sleep with the person's weighted GPA. So I organized this table into 4 categories for sleep: less than 5, 5 to less than 6, 6 to less than 7, and then more than 7. And I categorized the GPAs into less than 3.5, 3.5 to 4, and then more than 4. And this was my results. Notice that I have an extra column and row for the totals. Those are not part of the observed counts. Everybody's okay with that? All right. So what I need to do now is calculate my expected counts. So if I'm talking about something that has the probability that it is less than 5 and less than 5 hours of sleep and less than 3.5, well, we found 30 out of 110 was the probability that we had less than 5 hours of sleep. And 22 out of 110 is the probability that our GPA was less than 3.5. If I multiply those two things together, 30 over 110 times 22 over 110, that would be the probability that both of them happened. If I then multiply that by the number in our sample, that would be the expected number of that 110 that satisfied less than 5 hours sleep and less than 3.5 GPA. Or the easier way to think about it is the formula, row total times column total divided by overall total. That's the formula for our expected count here. Everybody's cool? Rip through that because I just did it all verbally. Blah, 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 blah. There it is. Row total times column total divided by overall total. Again, these are giving us expected counts. It is not a probability. Those aren't percentages. So if I do that for each cell in my table, for this cell I'd have 30 times 22 divided by 110. And the next one I'd have 28 times 30 divided by 110, et cetera, et cetera. Boom. There's my expected counts. Everybody's okay? I'll now calculate my chi-squared statistic the exact same way, but before I do that, I should confirm my two thingamajiggers. What do we call those things? Conditions, that's the word, thank you. So the large counts, if I look at here, 6 is my smallest observed count, or I'm sorry, expected count. That's still greater than 5, so we're good there. This is 110 students. 110 is 10% of 11,000, or I'm sorry, 1,100. Way more students than 1,100 in the world, right? So we're good on that condition. Blah, 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 blah. Calculating the same way. So if I do that, I do like 3 minus 6 squared divided by 6 plus 6 minus 7.64 squared divided by 7.64, and just kind of continue on. Everybody's good? So each one of these calculations, like 3 minus 6 squared divided by 6 is the 1.5, and I'm doing that for each calculation, and I record those in a table. Is that okay with everybody? Notice that this one comes out to be 0. That's weird. Why did that come out to be 0? Well, the observed count was 9 and the expected count was 9. Oh, okay, sure. Which one, or which category ended up contributing the most to my chi-squared? It was this one. More than 7 hours and greater than 4 GPAs was the one that was furthest, was the observed count that was furthest from the expected count. Everybody see that? So that would be my biggest contributor. Does that feel okay? That feels like a test question, doesn't it? Okay. When I add all those things up, I get 12.6. That's my chi-squared calculated value. And again, the question is, well, is that a big number or a small number? I need to compare it to something. So we'll compare it to the level of significance, but I also need my degrees of freedom for that. Now, the degree of freedom here is different because we have a two-way table instead of a one-way table, right? So it's just going to be the number of rows minus 1 times the number of columns minus 1. So in our case, we had 1, 2, 3 rows and 1, 2, 3, 4 columns. Don't count the totals. Easy to do that. So it'd be 2 times 3, 6 is my degrees of freedom here. Everybody feel good? Okay. So, again, we have some level of significance would be stated in the problem. If our level of significance is 10%, if we have a blah, 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 here we go. So it's like, what am I looking at here? Give me the one that I want. Okay. Where's the thing that I'm looking for? 6 degrees of freedom. Oh, that is, okay. So here's our 12.6, right? 6 degree of freedom curve. Oh, this is, what am I looking at here? I don't have any notes written down. I think this is the level of significance. So notice that this is our chi-squared critical value. 12.6 would be somewhere over here, right? In between 10 and 15, like halfway. So we see that the chi-squared calculated is greater than the chi-squared critical. This is just like running through P's, same idea, blah, 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 blah. Okay, this is our actual picture. So there's our guy. This is our level of significance here in green. There's our chi-squared statistic. There's our p-value. Notice that p is less than alpha. Or we could say that chi-squared critical is less than chi-squared calculated. Either case is going to be rejecting the null. Yes, sir? You don't. It would be given to you in the problem. We're just kind of describing what it means, though, because I think it helps you remember which one is which. All right. Let's do a numeric example together, yeah? You're going to like this one, though, I think. All right, there we go. Oops. All right. So, what we got here? Administrators at NDP want to know if they're selling the correct food in the vending machines. They install 3 vending machines in the lower, middle, and upper divisions that each sell chips, Pop-Tart, and gum. Then they count the total sales of each food type at the end of 1 week. Who can state the null and alternative hypotheses for this situation? Nate, give it a go.
The null is the one where like they're independent of each other.
Mm-hmm.
So wouldn't it be like that?
So this
Yeah,
is,
so would it be like
what is this stuff?
the food?
Yeah, the food in the vending machine is independent of
The where it is.
the school division or something. Yeah, good. And the alternative would be that they are dependent. Again, you'd state food type and independent or dependent of division. Everybody's okay? Okay. What's the degrees of freedom? it should be 4. 3 minus 1 times 3 minus 1 is 4. Calculate the expected counts. How do I do the first one? How do I do the first expected count for chip and lower? Divided by? Good. Row total times column total divided by overall total. Everybody's cool? Now, Mr. Kulik, that kind of stinks. I have to do that 9 times. You really don't. I'll show you how you don't have to do it in a minute. Okay, and then the last piece is calculate the chi-squared statistic. Let's show you what your calculator can do. What I'm going to do is I'm going to start by opening up a matrix. So I'm going to go to Edit. And in matrix 3, I'm going to make a 3 by 3 table because I have 3 row variables and 3 column variables. And type in the observed count table as shown without the totals. Second, and then the x to the -1 button. Yeah. So far, so good. Still doing good. How about now? Are we still doing good? And now? Oh. All right. Once I got that typed in, I'm going to exit out of there. And then I'm going to press Stat, go over to Tests, and go down to the chi-squared test, regular. That's option C. Select that. I'm going to tell it the matrix that I put my observed counts in. I'm going to tell it a matrix to put my expected counts in. It's going to do that for me. Ooh, thank you, Mr. Calculator. I just have to tell it where to put it. And then I'll hit Calculate. Look at what I get. It even gave me the degrees of freedom. Aw, thanks, Calculator. Gives me the chi-squared value, the p, and the degrees of freedom. All, and the expected counts, right? If I go back and I look at, say, matrix B, there's all my expected counts. Nice, right? Boy, that saves me a lot of button pushing. Now, in practice, if it says calculate the chi-squared statistic, this is what, and we're looking for some shown work, this is what I'd like to see. So you say chi-squared equals 30 minus, and then my first one was 28.8 or something, squared over 28.8 plus ... 80 minus, and then my last one was 67.4. Ah, come on now. Good golly. And then I forget what that actually came out to be. $13.5. So that's the kind of work that I expect to see for a problem like that. You don't need to write out all 9 of those things because boy, that's annoying. You show me enough that demonstrates you know how to do it, and then use the calculator to get the answer. Shh. All right. Everybody feel okay with this? Okay. I will load in these other in-class example solutions onto the OneNote, but I got some papers for you guys, some gifts.
I'm good. No, this is like, take it back.
You will once it comes time for the test. I'm glad that you did that. Sure.
Take it back.
Friday, we're gonna be doing the M&M activity, so if you don't
Do we get
like,
to eat them?
you can eat them when you're done, because like, who wants already handled M&Ms from someone else? Do I want those back? Probably gross.
This is the same thing you just gave us.
It is not the same thing I just gave you, it is slightly different.
They go to the bathroom as well.
Yes. One of the sheets is the goodness of fit test and the other is the independence test.
Are these, what are these two? Oh.
Let's go with Friday.
So if we
Did I give you an
determine,
extra?
We have homework
if we
online
determine
too.
this into.
You should bring that next time then too.
Bring that one too.
Yeah, that sounds
The
good.
one that
Do we-
some didn't turn us.
Do we have homework online too?
So the book problems you should do 3-1 and 3-2. There's 4 problems for 3-1 and 6 for 3-2. Use your calculator. Like they're not time consuming in that same way. Sure. Thanks.
So I just have like one more question. So for number 2 on this page, would this be a per t-test or a two-tailed t-test?
Do you have not equal to or do you have an inequality?
Like,
When you wrote your alternative.
I think it'd be not equal to.